Hi everyone, welcome to our video presentation about communication system. This video is proudly brought to you by students from RK93 Computer Network Engineering. Names are listed inside the video. The chapter that we are going to teach today is about amplitude modulation. We will talk about the concepts of amplitude modulation, the modulation index and the percentage of modulation index, sidebands and the frequency domain, and lastly the single sideband modulation. We are very sorry to inform our dear viewer that, unfortunately we are not going to explain further into the amplitude modulation power because of the lack of time and skills in video editing process. Thank you very much for clicking the view. Now we will begin our chapters. Amplitude modulation is a modulation technique used in electronic communication, most commonly for transmitting information via radio carrier wave. In amplitude modulation, the amplitude, which so-called signal strength, of the carrier wave is varied in proportion to the waveform being transmitted. From the graph, we can see very well the peak amplitude of the information signal is pointed. This is another graph about a carrier signal is being modulated, producing a modulated carrier signal. In amplitude modulation, it is particularly important that the peak value of the modulating signal, Vm, be less than the peak value of the carrier Vc. Vc is the carrier signal, while Vm is the modulating signal. Distortion occurs when the amplitude of the modulating signal is greater than the amplitude of the carrier. A modulator is a circuit used to produce amplitude modulation. Amplitude modulators compute the product of the carrier and modulating signals. This is the concept about how the calculation of the modulating signal works. Modulator must be able to produce mathematical multiplication of these two analog signals. We can see that the output of the modulation process is actually the product of modulating signal, Vm, and carrier signal, Vc. Mathematical representation is as shown. Now we will be talking about the modulation index. The modulation index, M, is a value that describes the relationship between the amplitude of the modulating signal and the amplitude of the carrier signal. M is equal to Vm over Vc. The modulation index, M, is also known as the modulating factor or coefficient, or the degree of modulation. The modulation index is recommended to be between 0 and 1. To find the percentage of modulation, simply times the modulation index, M, with 100%. In order to find the value of Vm, we use the formula as shown, which is V maximum minus V minimum over 2. To find Vc, the formula is similar with Vm, but the difference is, Vc is the summation of V maximum and V minimum. By substituted Vm and Vc into the modulation index formula, we get another simplified formula as shown. The peak change of modulated output wave, Vm, is actually the sum of the USF voltage and the LSF voltage, where VUSF is the peak amplitude of the upper side frequency in volts, while VLSF is the peak amplitude of the lower side frequency in volts. The expression of the formula are as shown. Now we will talking about the modulation index and percentage of modulation. The modulation index M is a value that describes the relationship between the amplitude signal and the amplitude of the carrier signal. The index is also known as the modulating factor coefficient, or the degree of modulation. By multiplying the modulation index by 100, will gives the percentage of modulation. The modulation index is commonly computed from measurements taken on the composite modulated waveform. The Vm formula using oscilloscope voltage values are as shown. The amount or depth of amplitude modulation is then expressed as percentage rather than fraction. This shown the voltage maximum and the voltage minimum. We are now talking about the overmodulation and distortion. The modulation index M should be around 0 and 1. If the amplitude of the modulating voltage is higher than the carrier voltage, M will be greater than 1, causing distortion. If the distortion is great enough, the intelligence signal becomes unintelligible. Distortion of voice transmissions produces garbled, harsh, or unnatural sounds in the speaker. Distortion of video signals produces a scrambled and inaccurate picture on a TV screen. This figure shows the distortion of the envelope caused by overmodulation where the modulating signal amplitude Vm is greater than the carrier signal Vc. We are now going to talk about sidebands and the frequency domains. Side frequencies, or sidebands, are generated as part of the modulation process and occur in the frequency spectrum directly above and below the carrier frequency. And the calculation part is easy. Upper sidebands equal to the Fc plus Fm. Lower sidebands equal to Fc minus Fm. For the bandwidth calculation, it is equal to F USB minus F LSB, which is also equal to 2 times Fm maximum. And this figure shows how a composite amplitude waveform is formed. It is actually the combination of the 4 waves: modulating signal, lower sidebands, carrier signal, and the upper sidebands. When we look into the time and frequency domain, we can clearly see how an amplitude modulation wave is formed with the 4 signal that we mentioned before. With the combination of modulating signal, the 3 frequency signal is then combined, forming a time domain wave signal. Now we are going to talk about pulse modulation. When complex signals, such as pulses or rectangular waves, modulate a carrier, a broad spectrum of sidebands is produced. A modulating square wave will produce sidebands based on the fundamental sine wave as well as the 3rd, 5th, 7th, etc. harmonics. Amplitude modulation by square waves or rectangular pulses is referred to as amplitude shift. Keying, ASK. ASK is used in some types of data communications. This is a figure about frequency spectrum of an AM signal modulated by a square wave. Note that the center is the carrier frequency, with sidebands produced on the left and right represent lower sidebands and upper sidebands respectively. The more harmonics it produces, the more sidebands it becomes. This figure shows the amplitude modulation of a sine wave carrier by a pulse or rectangular wave is called amplitude shift keying. 50% modulation is shown in red, while 100% modulation is shown in blue. For pulse modulation, continuous wave (CW) transmission can be achieved by turning the carrier off and on, which transmitting of Morse code by using dots and dashes. CW transmission is also referred to as on-off keying, OOK. Splatter is a term used to describe harmonic sideband interference. Now we are entering the last part of this video, which we talk about single sideband modulation. In amplitude modulation, 2/3 of the transmitted power is in the carrier, which conveys no information. Besides, signal information is contained within the sidebands. Single sideband, SSB, is a form of amplitude modulation where the carrier is suppressed and one sideband is eliminated. These are some types of the modulation signals. First, we have SSB. Single sideband modulation. Secondly, we have SSBSC. Single sideband suppressed carrier modulation. Third, we have DSB. Double sideband modulation. Fourth, we have DSBSC. Double sideband suppressed carrier modulation. Let us talk about DSBSC, which is the double sideband suppressed carrier modulation. To generate DSBSC signal, we need to suppress the carrier, leaving the upper and lower sidebands. This type of signal is called a double sideband suppressed carrier, DSBSC, signal. Signal information is contained within the sidebands, not carrier. Thus, no power is wasted on the carrier by suppressed it. Balanced modulator is used to generate DSBSC signal, produce the sum and difference frequencies of a DSBSC signal, but to cancel or balance out the carrier. Because of the difficulty to demodulate or recover at the receiver side, DSP and DSPSC signal is not widely used. This figure is about DSPSC signal. We can clearly see that the suppressed signal is in a dotted line, while both sidebands is conserved. Now we talk about SSB signal, single sideband modulation. Because information is contained within both sides of the sidebands, one sideband is all that is necessary to convey information in a signal. A single sideband suppressed carrier, SSBSC, signal is generated by suppressing the carrier and one sideband. The SSB signal have some benefits, which are: first, spectrum space is conserved and allows more signals to be transmitted in the same frequency range. Second, all power is channeled into a single sideband, producing stronger signal. Third, smaller bandwidth and less noise is produced. Fourth, less selective fading or cancellation over long distances. Well, thank you very much for watching. Have a nice day.